it is a short video in which I will explain how to build a neural network in Pytorch. Okay, so neural network comprises of layer modules that perform operations on data. Torch.nn space provide all the building blocks that you need to build your neural network. Torch.nn. Okay, so express that in torch.nn there are various building blocks for graphs only, right? So when I see the graphs also, it's a 3-dimensional, 1-dimensional, or maybe 2-dimensional, or maybe 3-dimensional graph. So it is in torch.nn library we can sing the building block of graph. So it is like containers. So containers contain module sequential, module list, module dictionary, parameters list, and so on. I mean, register module full backed hook, register a backward hook common to all modules, and so on. Pooling layers, it is added a one-dimensional max pooling layer over an input signal composes our input lines. nn.maxfull 1D, nn.maxfull 2D, okay, nn.maxfull 3D and something. Non-linear activation widget some non-linearity, it is nn.elu, nn.hard shrink, nn.hard swish, nn.prelu, nn.relu, okay, randomized leaky rectifier linear unit, or SELU function element wise. Sigmoid linear unit functions applies the sigmoid unit function. Software non-linear activation function are there. Padding layers or non-linear activation functions, and this it is all in torch.nn, right? Dropout layers, so dropout layer but represented by different thing. Distance functions, loss functions, and vision layer, shuffle layer, utility classes and function, okay, and quantize function, and so on. Okay, so I mean I will uncover this with the understanding of what is a dropout layer, linear layer, and sequential layer is there. So when I understand this particular torch.nn, so I see the containers convolution layer. So when we understand the basic building block of a graph, we talk about this. Okay, so naturally what happens that we talk about vertices and nodes and edges, weighted edges, degree of vertex, and subgraph, and connected graph tree, and directed cyclic graph, adjacent matrix, and adjacent list. Okay, so in Pytorch basically what we represent these all things in different in different way. I mean, node features, each node in the graph having associated features represented tensors. Tensors contain information as embedding and other event related to the node. Similar to the node feature, edges can also have features that can be represented as tensors. Okay. Graph structure, adjacency matrix, it is Aij, is set to 1, otherwise it is 0, right? Node from I to j, then the entry Aij is set to 1 or weighted node, otherwise it is 0. This is more efficient way to represent graph structure splitting sparse graph, which consists of 2 tensor, one for source node and another for target node, right? So layers designed to operate on graph data. These layers aggregate information on neighboring nodes to update the representation of each node. As I have already discussed in a previous research paper, there is a 2 node I and j, right? Message and source. Okay, there is an embedding and decoding embedding between the messages and probe, and between that. So I mean, a core concept in GNN where node exchange message with their neighbors to update their features on connected node. Message passing is there, and graph convolution neural network is there. Pooling layer, global pooling that is to aggregate nodes feature into a single graph representation. This can be done through min, max, or some pooling operations. Hierarchical pooling methods to create a coarser graph by pooling nodes based on certain criteria. Functions that measure how well the model prediction aligns. Loss functions. Okay. Optimizer, ADM, and SGD. Pytorch geometric data class, to hold the node feature, indexing and edge feature, transformation for processing the graph data such as normalization, argumentation, custom layer for building specialized GNN architecture. Okay, so what happened that we have studied different layers of that. Okay, so basic convolution operation, graph based basic convolution operation is performed by this two-layer graph convolution network, convolution neural network, right? So it is self.wait, self.reset parameters, def init, self in feature, out feature, super graph self.init, right? Def reset parameters self, okay, self x edge index, row column edge index, out torch.nn x self.wait, out row plus out column, right, return out. So there are different classes, and according to the classes we have functions, right? So it is like init function, reset parameter function, forward function, right? So we understand by this way, okay. So I will interpret it more, okay. So it is a padding layer, pooling layer, and we know that in convolution layer there are different kind of layer. So dropout layer is also there, and pooling layer is also there, and padding layer is also there. So in CNN there are layers, right? So it is convolution layer, activation layer, and pooling layer, and fully connected layer, dense layer, and dropout layer, and batch normalization layer, and flatten layer, right? So torch library can include all those layer. First is convolution layer, activation layer, okay, sigmoid layer 10a. Three of the most common activation functions are ReLU, sigmoid, and 10a. For sigmoid function we have function of x 1 upon 1 plus e minus x how to pronounce this, 1 plus e minus x, the power of minus x, and 10a it is fx equal to e power of x minus e power x upon e power x plus e power x minus x, right? So output values in 10a function is minus 1 to 1, right? In binary classification, whether it is 0 or 1, we have sigmoid function. In ReLU function, it is fx equal to max 0x, 0 to x. Have been reducing, vanishing, reducing gradient issue during in ReLU, right? Pooling layer is also there, which reduces the spatial dimension, thus decreasing the number of parameters in computation in the network. Max pooling, average pooling. A fully connected dense layer connected every neuron in the previous layer to the neuron in the current layer, combines feature learned in previous layer to make a final prediction, produce a vector that can be used for classification and regression in dense layer. A dropout layer, regulation technique to prevent overfitting by normally selected. So what fully connected layer, what is there? It connects every neuron in the fully connected dense layer is connecting every neuron to the previous neuron, okay. Combines feature learned in previous layers to make final predictions, okay. Produce a vector that can be used for classification or regression, okay. So what happened that vector can be generated which can be used for classification and regression. So output of that particular fully connected layer is same, that every layer is connected to previous layer and then previous layer to find out the output, whether it is a classification or regression, okay. So dropout layer, regulation technique to prevent overfitting by randomly setting a fraction of the inputs to 0 during training, okay. So batch normalization here normalize the input of each layer to improve training. Naturally, when the batches is created of the input output layer node structure, node architecture level, then we need to normalize the input from 0 to 1. Helps in addressing an internal covariate shift, making the training process more efficient, right? Flatten layer is convert the multi-dimensional input features input into one-dimensional vector. So there is multi-dimensional feature maps are there. We can convert into one-dimensional maps. Okay, so naturally it is import torch.nn as n, and import .pen function as f, right? So we have that class simple CNN nn.module. Then we have different layers. Out channels and in channels are also there. Kernel size is also there. Stride is also there. So what happened that fully connected layer is this f.relu self.fc2x return x model simple CNN print model. Okay, the various layers in CNN work together to process and learn features from the input data. By stringing multiple conversion pooling layer, CNN can capture increasingly complex pattern, making them particularly effective for tasks like image classification, object detection, and more. Okay, so this is how Pytorch can work. More observations can be done. In understanding how these things are, activation functions are already there. Okay, and when I study whole parameters in lists, whole submodules in dictionary, in sequential container. Okay. So this is how a transformer model is an encoder level, decoder encoder layers and decoder layers. Okay, dropout layer is also there. Okay. So embedding losses as from either -1 or 1 or -1. Okay. So this is how it is. When I study the torch.nn, that I find out some certain things. That's why I mentioned. Okay, so when we form a neural network using Pytorch, so we check for the device. If CUDA, then if torch.qda is available, else maps. If torch.backend maps is available, else CPU. Okay, what happened that if the CUDA is available, then it is if torch.backend is map MPS is available, then it is CPU. Whether it is a CUDA, then MPS, then CPU, right? If CUDA is available, then it is fine. Else MPS is available, then it is good. Else CPU is available, right? So it depends on device. Class, we have to define the class by subclassing the NN module. Okay. NN module we supplying, and in init function we define the neural network. Every NN module supplies including operation and input data in the forward method. So in forward method we can define the input data. Self.flatten x logic, self.linear RLU a stack products return logics. NN.linear this dot NN.RLU NN.linear NN.RLU NN.linear. Okay. So we can see rectified linear unit, and we can see that in 28 into 28 pixels 512 NN.RLU in 512 into 512. Okay, then we have 512 into 10, right? Okay, so it is a 576. It is a 576. 28 into 28 pixels. So naturally it is 576 also. It is a 576. Yeah, so it's 784. Yeah. Cases all these cases wrong, but not so. It is 784 into 512. Okay, NN.RLU NN.linear NN.RLU NN.linear. Forward this model neural network dot device print model, right? So when we print model, we create an instance of neural network and move it to device and print its structure, right? So from this code, neural network dot in model, we have created a structure of that particular neural network. Okay, NN.RLU NN.linear or 784 frames of 784 into upon 512. And it is 512 into 512, right? 512 into 10. Okay. For input data. Okay. So torch.rnd 12828 device is device, logic model X, softmax is this, predict is this, input image torch.rand print out input image to size this, right? Okay. finish as a flatten convert that each 2D image consists 784 pixels. The mini bias dimension is maintained, right? So we can flatten that particular image to 2 dimension to 1 dimension by nn.flatten, and we have that class which is already there, and nn.relu is already there, softmax is already there, minus infinity to plus infinity, pass to nn values is scaled from 0 to 1 values. I mean softmax can handle the values from 0 to 1 only, right? Okay. Model parameters, many layers inside an inner we are parameterized. So this. Okay, then we got a layers, linear RLU, stack 0 bit, size, torch size, and values, right? So when we got the values, we can see the negative values, positive values, and layers. Okay, and that's all we got it. Okay, so it's a simple designing. First, what we do that we can call the torch.nn. All the building blocks you need to hold in torch.nn is the foundation which provides everything. Dropout layer and the layer which is comes in convolutional neural network. So every layer or between the layer, different type of layers. So torch.nn has documentation of that. Every module in Pytorch subclass the NN module. Neural network is module itself. You can say other modules. The next structure allows for building and managing complex architecture easily. Okay. So import OS, import torch, import from torch, import NN, from utils or data, import data loader, from torch user, import dataset and transformers. Okay. So naturally, what happened that it is a 784 and 512 first linear, then it is RLU, then it is linear, it is 512, then it is RLU, then it is linear again. Okay. So why we follow a particular models? Okay, by this way only. I mean naturally what happened that when I understand the flatten, so from 2D to 1D we use flatten, right? Then self dot linear RLU stack and dot sequential. Okay, so we coded from sequential level. Okay, so it is 712, 78, 512 or 512, right? So naturally what we started that we need to put that into linear frame only. So you can say the pattern that how that particular function, that is self dot linear RLU stack or n dot linear sequential, is arranged. I mean naturally what I see that we are trying to put it in a single layer or single output. Flatten is MNST dataset image, so we have 512 neuron in the first hidden layer, right? Okay, so the option of price RLU we applied for maximum is 0 to x, non-linearity, one dimension 0 to x. Naturally one dimension, for one dimension we apply nn.rlu, right? And nn.linear we applied for fully connected layer. The input size is 512 correspond to output of a previous layer. Output size is 512 neurons in the hidden layer, right? So what happened that earlier we in first step that is nn.linear, we have 784 pixels. Means the model is accepted to be flattened. Output size is 512 neurons in the first hidden layer. In RLU, what happened that RELU functions, maximum function is 0x to introduce the non-linearity, complex when it non-linear patterns. nn.linear 512 into 512. Okay, so this is happening. This has already happened. Fully connected layer. Okay, I mean in dot linear we have this 512 second hidden layer. 0 to 9 representing 10 classes of classification, 0 to 9 in the MNST predecessors. So what happens that linear can maximum is 0x and linear can do 1 0. Okay, RLU function applied to output of the second layer. Yes, I mean output of the second layer it apply that we can get the input of the first layer and output of the second layer from the RLU function. Okay, I mean RLU function can get the output of second layer every time when it get called, right? Okay, so I mean it is like 28 and 28, 576, 512. Then we call an RLU function which can get the output of previous layer, which can act as an input of second layer. Okay, then it is a linear 512 into 512, and what happens that it is a, again we have that RLU. Then we have it is 10 whether that particular image is that particular object is one that is that this or this, right? From that NN.DNA we try to find out that we start from 786 pixels, come into 512, 512, 512, then we go into 512 into 10, right? So naturally it is the understanding. Okay, forward pass is this self x logit self dot linear RLU stack x return logits. So what happened that naturally we return the images or return the particular you can say particular image or object, right? Whatever we want to call, right? So model simple and input data torch.nn. Okay, model input data print output, right? So I mean this how this is working in same logic. Okay, so we can create an instance of neural network in model, right? Model from model we create an instance. Device we have already called layer. Okay, so model layers it is inputs image torch or random 388. Okay, now what happened that we have created a model model layers also. We have created a model which is again a replica of a neural network which is already created. Okay, so from n dot flatten and n dot linear we have created this n dot RLU. So n non-activation encompass model input of the player after linear transformation. Okay, so dot sequential standard softmax and model parameters. So what happened that initially we have created till instance we have created, then we use a model to pass the input data, right? This execute model forward along with the background operations. Do not call this model dot forward. Okay, so what happened that okay, this way when I study this, so this can also be studied. This is def register module backward hook, right? So what happened that it is like import torch parameters are there, hooks are there. Import torch or util dot hooks as hooks. It is a part of library function hook. Okay, from typing import union tuple can you callable. Okay, and so on. So split if you don't okay, so this way it is happen. What we can do, okay, so not naturally what happened that it is a dictionary. I am reading that particular Pytorch torch and modules.py, right? So so yes, that is how it is happening. That we got model layers, right? So we let's break down to that. Understanding is the calling the model on input 2-dimensional tensor with dim 0 corresponding each output 10 raw vector value for each class and dim 1 corresponding to individual values of each output. We get the production probability by passing through the n softmax model. Torch or and 128 device Alex probability and its softmax dim logics for predict print effortless by predict, right? Okay, so this already done. What we have prediction of y predict. Softmax option is used, and this is used. N dot flatten is there. Flatten n dot flatten image is this. Flat image dot size, right? Layer 1 n dot linear in feature out feature. In feature and out feature. To see the standard variant biases and then represent that. Okay, so each size of each input symbol and size of each output symbol. Okay, so bias is there. Input of which is represented by this, output feature is represented by this. Okay, I mean how output feature is generated by y equal to x, a transform plus b, right? So naturally what happened that it is biases is there and y is there and x a transpose is there, right? Okay, so naturally what happened that this module support TensorFloat 32 in different precision. So I mean we got it from understanding that it is 20, 30 and 128, 20 and so on, right? So this is again this way. Okay, so out features, in feature, out feature is there, right? Hidden layer is there, hidden size also we have printed. Okay, so based before RLU and after RLU we see the tensors pattern, and we can have the observations. I mean in inline it is softness function can help in 0 to 1, because minus infinity plus infinity is again an issue. I mean in software function we can provide it that into 0 to 1 naturally. Okay, so what happened that model structure param in model named here name size param size dot value upon and right. Okay, so I mean this is linear feature 788 out features 5 and 2 bias true bias true bias true. Okay, so I mean this happens. Okay, our linear RLU stack tensors doing that. Okay, so I mean this is how the neural network can be built and understand neural network using Pytorch, right? So thank you so much everyone. I will post the link of that